Session 2009, exercise number 2. The aim of this exercise is to measure the speed of plane using the phenomenon of electromagnetic induction. And here we have in the part A, motion of a conductor in a uniform magnetic field. So you have here, must pay attention to, it's a uniform magnetic field. A homogeneous metallic coil Mn of length L slides on two horizontal and parallel metallic rails, A prime and E prime, at a constant velocity. So we have a constant velocity. During its sliding, the rod remains perpendicular to the rails and its center of gravity moves along the axis OX. At t equals to 0, G is at O. So this means we have x0 is equal to 0. And at the instant t, the abscissa of x is OG, where V is dx over dt. The whole set is put within a uniform magnetic field B, perpendicular to the plane of the horizontal rays. So the first part is determine at the instant t the expression of the magnetic flux crossing the surface in terms of B, L, and X. And they are giving us the positive direction. So according to the positive direction chosen, we have the normal is perpendicular down. So in order to find in the first part the magnetic flux, this is phi equal to N BS cosine theta. But we know that we have only one loop, so it's equal to B. And the surface of a rectangle, it's equal to width times length. So the surface is width times length, which is equals here. If you notice, the width itself is x. It's this one, this is the width, and the length is mn, so it's L. So we'll get here x times L, and the angle theta is the angle between B and N, which are B and N are here opposite direction. So it's equals to 180. So the answer will become B times L times X times cosine to 180, which is equal here minus 1. Then we'll get minus B L times X. Now, second part, explain the existence of an induced electromotive force across the ends of Mn. In order to have electromagnetic induction phenomenon, in order to have electromotive force induced, we must have the phenomenon of electromagnetic induction. So here, if we notice, phi is equal minus B Lx, and we know that x is variable. So here I can say that phi equal minus B Lx, x is variable due to the variation of the surface, this means. So x is variable, this means that phi is variable. And if the flux is variable, this means I have electromagnetic induction phenomenon exists. Which means that an electromotive force, induced electromotive force, exists between M and N. Next question, determine the expression of the induced electromotive force in terms of B, L, and V. Now we know that according to Faraday law, we have E equal minus d phi over dt. We already said that phi equal minus B L times X. So it will be minus, so equal minus. And here we'll do the derivative, but I have B and L are constant. So this means it will be minus and minus, then it's plus, and B times L dx over dt. Dx over dt, this is what you call the speed. So it's B L times V. This will be the electromotive force. No current will pass in the rod. Why? Now, if we look at the figure, the circuit is open. So even if I have a induced electromotive force, but mind the current, there's no flow of electrons. So like in the part 4, since the circuit is open. Now part 5, deduce the polarity of the point M and N of the rod and gives the expression of the voltage U and M in terms of E. Now, in order to find the polarity, I can look, for example, if I had a current, then the current will have the same sign as E. I have E, which is the electromotive force is positive, which means if I had a current, the current would be positive. If the current would be positive, then it will be with the same direction as positive chosen. And we know that that positive direction chosen was like this. And this was here the point N, sorry, this is N, and this was here the point M. So this means If the current was in this, if there's current and the current was in the positive direction chosen, then this will be the direction of the current. And we know that the current بيطلع من positive and then negative. This means since it's going out from N, then N is the positive part and M is the negative part. So as polarity, I can say that N is negative and M is positive. And the question also is to find the expression of the voltage U and M. So in order to find U and M, we have U and M equals. Now here I have U and M and there's open circuit. So usually we say U and M equal. Usually if you have a closed circuit, we say U and M equals to minus Ri plus E. Here in this case, we will say that U and M equal Ri minus E, which will become U and M equal to minus E, which means equal minus B L times V. And this will be here the expression of U and M. Now we continue. A plane is flying horizontally along a straight. Now we are doing an equivalence between this figure and the figure before. A plane is flying horizontally along a straight path with a constant velocity v1 within the uniform magnetic field of the Earth. The vector B in the region has a horizontal component of magnitude. We have BH equal this much and B vertical. These are the magnetic field of the Earth. So the horizontal and vertical components. The wings of the plane consider a straight and horizontal conductor of length L prime. So هيدي اللي كانت MN قبل, so it's now MN prime. It's a conductor where we have the length. It sweeps with the time of surface area. So it changes with the time. It moves. 1A, the magnetic flux of BH through the swept surface area is 0. Why? So in order to find the magnetic flux, we can say that the flux is equal to NBS cosine theta. Here we are taking BH. So cosine theta, theta is the angle between the normal and BH. And we know, we already said before, when the positive direction was like this, that the normal is down. So the angle between both, between BH and N and the normal is 90 degrees. And cosine of 90, so here we'll get NBHS cosine 90. And cosine of 90 is equal to 0. So this is why the flux is 0, the flux of BH. Now part B, give the expression of the induced electromotive force, E1, that appears between the ends M prime and N prime in terms of BV, L prime, and V1. So first, we'll say that F phi is equal to B and BV times L times cosine theta. N is equal to 1, so we'll have BV times, sorry, this is S here. So times S times cosine theta, and S is the length times the width, so we'll get L times X, and cosine theta, it's the angle between BV and the normal, and they are both parallel, BV and the normal, parallel, same direction. So we'll get here cosine 0, and this is equals to 1. So the answer will become BV times L times X. Now we want to find the expression of E1, the electromotive force. So also according to Faraday's law, I have E1 equal minus d phi over dt. So by doing the derivative, we'll get minus BV L dx over dt, and this is what we call the speed, minus BV L times V. Now, part 2, determine V1 if the potential difference across the wings has a value of 0.36 volts. So, in order to find the potential, in order to find V1, I must have, so we have BV, we have the length. The question is to find the speed V1. So, do we have E1? So, E1 is equals to who? We already said, so if I want to find U and M, it's equals to minus E, which is equals here to BVL times V1. And this is equal to 0.36 volts as given. This is the voltage. So I have BV, it's equals to 4 times 10 to the power minus 5. We have the length of M prime and prime is 30 meters times V1 equal to 0.36. And here we can find V1 which will become equals to 300 meters per second.